Hello and welcome everybody back to the Genomics Boot Camp, where we speak about genomics from the beginner's perspective. My name is Gábor Mészáros and we will be looking today at genomic text files. Because, well, indeed there is a lot to learn just by looking at these files, and from this video you will find out what it is. So enjoy!
The data that we will be looking at is from the Dryad repository, which is a place where you can obtain freely available data that you can use in your analysis. Of course, if you use any of the data in your analysis, you need to cite them appropriately, including the accompanying paper. The first data set we will be looking at, and also that we will use further on in our exercises, is from Jolly et al. From data from the publication Signatures of Selection and Environmental Adaptation across the goat genome post-domestication. So you can go ahead and download it via the download button on the right side. The other data set we will be looking at in this video is from the publication from Decker et al. Worldwide Patterns of Ancestry, Divergence and Admixture in Domesticated Cattle. Likewise, there is a download button and you can download this one as well. I selected these two publications or data sets because one of them is having the data in the Plink binary PET format, and the other one is having in a classical Plink PET and map format, which I consider as the two most important data files or data formats in Plink. And so in this video, we will go through these files to see what which kind of data is available to us. So the binary PET files with Plink are consisting of three files. There is a file name that is the same for all, and then there are file extensions BED, BEAM, and FAM. And so these three files should be, or I would say must be, in the same directory, so you can conduct the analysis that you want to do later on. But if you open them, so the first one is a list of animals, and basically, so this has always this kind of a format of 6 columns. Each row here is an animal. So if you see how many rows are in your FAM file, this is the number of animals you have genotypes for. So this one is, I would say, a very large data set with 4,653 animals in them. The columns themselves, they also have their meaning, and well, you can also review this meaning on the Plink website in the help files. But for now, I would just add a few comments on that. So the first column is the so-called family ID that is, well, used for designation of larger groups. So Plink was initially developed for human data, so also that's why the terminology is also human related. But of course, well, you can use it for any other kind of data like microbes, animals, plants, etc. So we will stick to the terminology family ID or FID, but it can be used for many other purposes, for designating, let's say if you talk about animals, it could be countries, farms, regions, or breeds and similar. Also in this case, the authors decided to go with the using of this column for breeds, and so there are breed abbreviations from all around the world, and in the publication you can actually find out what these abbreviations mean. The second column is also very important, is the so-called individual ID, and it should be unique for each individual, for each animal in this case. The next two columns are the ID of the father and the mother of the individual, which is stated in column 2. Now, this is frequently either it's not available or whoever puts the data together does not consider it to be important. So it designated as unknown. So that is why there are zeros here. The fifth column is the sex of the individual. So I believe 1 should be for males, 2 for females. And if 0, that is also, well, just saying that is not available or missing. The last column is the phenotype column that is related to this individual again in column 2, but also in this case, as it happens, it's either not available or not important for this purpose, so it's denoted as missing. This could be also with 0, but most often it is done with the -9 being the code for the missing phenotype. The next important file is the BIM file, which is basically the map file. In here, each line is one SNP. And again, if you look at the file and to see how many lines we have in the BIM file, so you see here is 53,347. That means that this many SNPs we have in the dataset. So just by looking at these two files, so by looking at the FAM file, you see that this many animals, more than 4,600 animals, and more than 53,000 SNPs are in this dataset. Again, the BIM file has a fixed structure. The first column is the chromosome where the SNP is located, and it starts with a 0. Well, of course, there is no chromosome 0, but these are the so-called unplaced SNPs that are appearing on the SNP chips. But if you go a bit lower, so you see then that it starts with chromosome 1, 2, 3, and so on, and goes up to the last autosome and chromosome 30, which is the sex chromosome or X chromosome in goats. So the second column is the SNP ID. That is again unique for each SNP, and it is was given by the people who designed actually the SNP chips. The third column is the position of the SNP in Morgans, which is often left as a 0. It's often regarded as uninteresting and therefore zeroed out and skipped. The column 4 is actually the one that is more important. This is the position of the SNP in base pairs. So let's say we have this SNP here, and so this is located at the position 31,650,000 and something. Which is meaning so that this is the SNP position from the beginning of chromosome 1. So where we actually know exactly where it is located. The counting starts again from 0 for each chromosome. So this is not from the beginning of the genome, but from the beginning of the chromosome. So as you see here, at the end of chromosome 1, there is this is the last SNP at chromosome 1, and then chromosome 2, the counting starts again. The nucleotides here show that which SNPs, or what are the genotypes of the SNPs located on the genome. So this is, for example, an AG SNP or CA SNP and so on. Also from this BIM file, we see that the genotypes are in a nucleotide coding, so not numerical or not any AB coding. The last file that we need to talk about with the binary PET format is the so-called BET file, or the binary PET file, which is actually where the majority of the data is located, but it is actually, well, as the name says, a binary file, which is very well readable for a computer, but it doesn't tell too much for a human eye. But for the purpose of this video, we can open it. So, well, we cannot see much here, but for the computer, it's actually in a format that it can process these data very efficiently, quickly, and also it doesn't take up much space. So you see that this is 4,000 genotypes are taking not about 62 megabytes. So this was it for the binary PET format. And well, we look also at the classical PET and MAP format, which is both of them are actually text files. So you can actually read the full data in, well, with the text editor, or just looking at them. So you actually also can see the individual genotypes as well. Also, well, we have here also a map file and the PET file. So these are the two that are most important. Again, the file name is the same, and the map and the PET, the file extension is which is the most relevant. If we open the map file, we see quite a similar picture as before. So the first column is the chromosome, second column is the SNP ID, the third column is the position in Morgans, and the last column, or the fourth column, is the position in base pairs. Here, well, there is a zero chromosome, then, but it's just one. That already gives a clue that something happened in this file. And also, if you scroll at the end, and knowing that the sex chromosome in cattle, so this is the cattle data, and the sex chromosome would be 30, but the 30 is also missing here. That also already gives a clue that it's this data set might be pre-processed. And if you look at the details in the downloaded files, you indeed find out that this data was already quality controlled. Well, this map file, you see that it's quite similar to the previously to the BEAM files. I can put them near each other. So it's yeah, basically the map file is the first 4 columns of the BEAM file. So the genotypes of the SNPs are not listed here, but otherwise is the same. So if you look at the number of lines in the map file, in this case 43,043. So this is the number of SNPs for which we have the genotypes for. But unlike the binary PET files, you can actually look at the individual genotypes in this format in the PET file. So we open that, and it might take a bit longer because of this fairly large file, but this is why you need a proper text editor for opening these big files. So the TextPad I'm using is quite good. So anyway, so what we see here is, well, a lot of numbers, but so in the PET file, again, if you see or if you consider it as basically a paste together of two files. So this is actually the first 6 columns. The first 6 columns are basically the FAM file from before, and also, well, the column designations or the column names and functions are the same. So this was the FAM file from before, obviously for different data sets. So the individuals doesn't match, but so you see there are the 6 columns I was talking about, and we have a very similar 6 columns also here. Well, you see, so there is the family ID, which is in this case, it was used as like a numerical coding, but still they are, I believe they are denoting some breeds. Also, the coding, for the coding, you can consult the paper, the accompanying paper for this data set. The second column is the individual ID, the father and the mother, or the sire and the dam information here is also unknown. Here, the sex information is 1, so we know that these are all bulls. Bulls again, because we know it's cattle data. And the phenotype is unknown. But unlike the previous case, what we can see actually is the actual genotypes. So here again, one line is one animal. So by looking at the number of lines in the PET file, we can see that there are 1,543 animals in this data set that are actually genotyped for these 43,043 SNPs. But in this case, the SNPs are actually, well, the SNPs are starting directly after the FAM file. So already basically these first 6 columns. So column 7 is already a SNP, but it's not like one column being one SNP, but each 2 columns are being a SNP. So this is the first column 7 is basically the allele 1 of SNP 1. The column 8 is the allele 2 of SNP 1. So what we know that this first animal, this is being homozygous. The next 2 columns are SNP 2. The next 2 columns after that are being SNP 3 and so on. So what we can see that, for example, all of these animals are homozygous for SNP 1, this one being heterozygous, let's say for SNP 1. So actually what we can see is the actual genotypes for the animals. Again, a striking difference compared to the previous data file is that what we see again, that the coding of the genotypes in this case is not nucleotide coding as before. You remember before it was A, C, and so on. So basically it were nucleotides, and this is actually a numerical coding. So the number 1 is used for allele 1, and the number 2 is used for allele 2. So this also tells us something about the coding style. And if you let's say if you would have 2 data from 2 cattle data sets, and one would be nucleotide coding, and this would be numerical codings, and you cannot merge them directly, but you need to do some kind of adjustments before you can do so. So that's why actually after you receive the data, the first thing that you need to do is open them and see what is in them by looking at the number of SNPs, number of animals, the coding type, and so on. So actually you have a bit of a feel what you have to work with.
So this was it for now, just looking at the text files and to the genomic data files. At some point we will get also to create them and manipulate all these large quantities of data. Yeah, so for that I just encourage you to push the subscribe button so you are notified when any of these future awesome videos come online. For today, I thank you for your time and have a nice day.